Hi guys, in this example I'm going to go through how you can know how to calculate the test statistic, which is one step in the entire hypothesis testing process. So this claim says fewer than 95% of adults have a cell phone. Just let me write that down. The claim is that less than 95%, so that's a proportions claim. 95%, less than 95% of adults have a cell phone. In a reputable poll, p hat is out of 1,156. There were a certain number of people who said that they had a cell phone, and that turned out to be 88%. So this is 0.88. Now, if I need to, I can figure out what x is by solving for x. So to solve for x, I could just do x equals 0.88, 88% of the total sample size. Oops, I have a visitor. So I don't think I'm going to actually need that for this problem. So I'm just not even going to do it. But I'm going to keep in mind that the claim has no equality, right? Strictly fewer than. So that means that my claim would be p equals 0.95. My alternative would be p is less than 0.95. So this would be a left-tailed test. And I would need to know the alpha in order to know what my critical value is, but this would be my alpha on one side. That's not really relevant for being able to calculate the test statistic, but I thought it was a good opportunity to review setting this up. But to actually get the test statistic, we just take the sample statistic, which is p hat. P hat is 0.88, and we're going to turn that into a z-score using the test statistic formula, which is in the reference packet. So the formula is z equals p hat minus p over the square root of pq over n. All right, so what we do is we take our 0.88, we subtract the claimed value. So remember, whenever we're calculating a test statistic, we're doing it under the assumption that the null hypothesis is true. So remember, since the claim is that fewer than 95% of adults have a cell phone, the null hypothesis is that the percentage is actually equal to 0.95. So if we assume the null hypothesis is true, then we assume that p equals 0.95. And that's the reason that we use that right there. And then we go and put 0.95 times 0.05, because q is 1 minus p, divided by n, which is 1156. Right, so we'll calculate that, and that'll be the answer to our problem. All right, so the answer turned out to be -10 to 2 decimal places, -10.92. So that's the actual test statistic. Now, it's not part of what we've been asked to do, but I just want to tell you that that is an extreme z-score, right? We know that. Z-scores tend to be within, right, 99. By the empirical rule, we know that the vast majority, almost 100%, even more than the vast majority, almost all of the z-scores should fall within 3 and -3. So to have a z-score that's -10, that's really, or actually almost -11, it's really, really far back. And it's going to have an area under the curve that is so close to 0, you might as well call it 0. And what else is interesting about that is it's going to beat any significance level. it's definitely going to turn out that we will reject the null hypothesis, and since the claim is in the alternative, we would support the alternative hypothesis and support the claim. All right, then the second example here, claim the mean pulse rate. Okay, so now we're talking about a mean. Here we were talking about a percentage. Here we're talking about a mean. So the claim is that the mean, notice we always use the population parameter, not the sample mean, x bar. The mean pulse rate in beats per minute of adult males is equal to 69 beats per minute. That's the claim. So the claim has equivalence, so actually the claim will fall into the null hypothesis. And the alternative is the complement of the claim. This is a two-tailed test. Not that it matters for this, we're just being asked to calculate the test statistic. Now, whenever we calculate a test statistic, again, we use this assumption. We assume that the true mean is 69. We do it under the assumption that the null hypothesis is true. And if the null hypothesis is true and our test statistic is really extreme, then that means it's extremely unlikely that we would have these results by chance. Okay, so then we use the test statistic formula. So this time we were dealing with a sample of 134 adults, a mean pulse rate from the sample, so that's x bar, and a standard deviation. We're still talking about the sample, so that would be S, not sigma. And since we know S rather than sigma, that means we're going to use the t distribution. So there's two choices for the test statistic formula when you're doing a claim about a mean. One of them involves using sigma, and the other one involves using S. The one that involves using sigma, the true population standard deviation, will give you a z-score. And when you're using S, the sample standard deviation, you will get a t test statistic. So we're doing the one with t is x bar minus mu divided by s over the square root of n. So this is according to the central limit theorem. We have 68.6 minus 69, assuming that the null hypothesis is true, divided by 11.3 over the size of n, sample size n, which is 134. So let's calculate that. So that works out to be negative 0.9, negative 0.409, okay, so 41 to 2 decimal places. Okay, so that is your test statistic. And that's a that test statistic is kind of close to 0, which is in the center of the t distribution. So most likely we would fail to reject the null hypothesis. The reason I say most likely is because this is not an example where we've been asked to conduct the full hypothesis test. If we did conduct the full hypothesis test, we would need to know the level of significance so that we could find the critical value and compare it with the test statistic. So before I close this video, I'm going to turn this into a full test so that you can see how this is relevant. So we know that the objective of this question was just to calculate the test statistic, but in context of doing a full hypothesis test, we would say that the claim is that the mean is equal to 69, so that the null is the claim. So if we reject the null hypothesis, then we would also, in effect, be rejecting the claim. The alternative is the complement of the claim, and that makes this a two-tailed test with a critical value on each side, positive with alpha half to the right, and a negative critical value with alpha half to the left. This is a t-distribution because we don't know 0, we don't know sigma, unknown. So we just use S, which is 11.3. And this is a t-distribution, right? So that makes my critical values t-scores and also my test statistic a t-score. So I would look in the t-distribution table. Let me look it up. Okay, so to look up my t-score in the t-table, I'm going to look up an area. Well, first we need to know alpha. So let's say we're told to use, let's use alpha equals 0.10. So that would be 90% confidence if it was a confidence interval test. It would mean that I have a total of 0.10 in both tails together, but 0.05 in each tail. And so when I look up an area of, or when I look up in the t-table, the column that has 90% confidence, 0.05 in a single tail, 0.10 total in two tails, I'm going to look with degrees of freedom. So this is 0.05 to its right, and then the degrees of freedom, which is n-1, would be 133. And the closest one in my table is 100 degrees of freedom. So that would be a t-score of 1.66 and negative 1.66 on this side. Okay, then I did my test statistic. I found my test statistic was negative, right about there, negative 0.41. And that means that my test statistic is not as extreme as my critical value, so it's not significant. And we would fail to reject the null hypothesis, which means we fail to reject the claim. So because we fail to reject the null hypothesis, since the claim is the null hypothesis in this case, we will also say that we have failed to reject the claim. And that's it for this video.